Video 2 of Chapter 8. We are going to focus on the idea of confidence in this video, both theoretically and in an application way. So in the previous video, we talked about what in general a confidence interval is and how do we create a confidence interval in general, that we start with some point estimate, a value from our sample. We apply a margin of error in both directions, an equal amount in both directions, and that gave us our lower and our upper range of values that created the entire confidence interval. And we were hoping that this confidence interval was going to successfully capture the true population value. Now, in addition to focusing on confidence, the idea of confidence is really used within the margin of error. And the margin of error breaks down into this idea of how much spread is there from the point estimate. That's really our margin of error. How much spread is there? But that how much spread can be broken down into two components. The how much part, which is related to our confidence level, that percentage, like 95% or 99%, for instance. And then the spread component, which really is our standard deviation value. Now, we'll talk about the spread specifically when we get into the specifics of how do we actually calculate a confidence interval. Now, what does it theoretically mean when we say we are 95% confident? What is that 95% really telling us theoretically and statistically? And so in order to really see what 95% confidence really means, we need to not just look at one confidence interval, but we're going to look at many confidence intervals. We're going to use this applet to really explore what it means, truly means, theoretically, to be 95% confident, or really any percent confidence. But we're going to focus on 95% because it'll be a common confidence level. Now, what I've done here is I've set this up to explore our marathon proportion data, where we were looking at what percent or proportion of runners were from the home state of Nebraska. So I put in here, and typically we don't know what this number is, but we knew that 44.5% of all the marathon runners were from Nebraska. I know what the population size is, and we're going to use samples of size 30. And initially, we are going to just do one confidence interval at a time. We are going to use a 95% level. So if I were to say, hey, make me a confidence interval. So here's that confidence interval. And notice there's a little dot right here, right where my cursor's at. And there's this black line that pops into play, and it says 0.446. Well, that is our population, our true population proportion, but they just rounded it to 3 decimal places, okay? So this is the true population value. And here is our confidence interval. Again, the little dot represents the sample proportion that was taken from the random sample of 30 runners. And if I click on this confidence interval, it will tell me that that midpoint, that sample proportion, so out of 30 runners, it found that 43.3% of those runners were from Nebraska. Now, the creation of the confidence interval itself is saying that we are 95% confident that the true proportion of all runners that are from Nebraska is between 25.6% and 61.1%. So what I want to know is, did this confidence interval successfully capture the true population proportion value of 0.4456? And it did, right? Because this interval, it's saying here's the true population value, and it is within this range here. So I want you to notice that it is green, because when the confidence interval is green, it's going to mean that it successfully captures it. So what color are we going to see if it doesn't successfully capture it? We will get there when it pops up. Now, a couple things I want to point out in the results section down here. The first part is really me doing one sample at a time. And then what it's also going to do down here is give me a cumulative total. So if I said, hey, let's take another random sample and create a confidence interval. Ooh, we already see one that's not meeting our criteria here. So this one says it is 0 for 1. And if I click on it, It says the midpoint, so it took another random sample of 30 runners, and it found that 66.7% of those runners were from Nebraska. So once we apply the 95% for the margin of error here, then we get a confidence interval from 49.8% to 83.5%. So is this confidence interval successfully capturing the true population value of 44.6% in this case? And it is not. So notice that it is red when it does not successfully capture that value. So cumulatively, we're batting 1 for 2 here, right? Our first one was good. Our second one was bad. So what would happen if I were to keep taking more and more and more and more and more and more samples? So let me let's go all the way up to 50 here. And you'll notice most of them on your screen are the good green ones, right? But every once in a while, we've seen a bad red one. Well, I'll tell you what, I've already passed 50, so let's go up to 100. Now, this gets kind of boring to do one sample at a time, but stopping at 100 confidence intervals, where are we at so far? We've hit exactly 95, which I will say is a little surprising to see that 95% number. Typically, we would see something near 95%. And so if I were to keep going, let me start. So now notice I'm at 95.5%. What I should start to notice theoretically is the more and more and more and more confidence intervals that I create, the closer this cumulative number is going to get to my confidence level. And you might say, well, when you were at 100, you were already at exactly 95%. Why would you keep going? Because now we broke 95%. And that's just going to happen. We're going to keep kind of deviating above and below 95%. And for my calculus people, really we're looking at a limit here. The more and more samples, the more and more confidence intervals that create, the limit of the percentage of all of those confidence intervals that is successfully capturing the true population value should approach the confidence level number specifically. Now, what gets kind of cool is if I said, hey, what if instead of just doing one sample at a time, what if I started doing 100 confidence intervals at a time? So here's 100 confidence intervals. And we notice most of them are green, right? Because we're doing a 95% level. We would expect around 95% of all of these confidence intervals to successfully capture the true value. And again, I told the applet what the true value was. So we know if it's successfully capturing it or it's not successfully capturing it. The thing about confidence intervals is, in reality, we don't typically know what the true population value is. So we won't know if we have calculated one of these good green ones or one of the bad red ones. That's the gray fuzzy area of statistics. So the confidence level interpretation says whatever percent you're saying the confidence level is, whether it's 90%, 95%, 99%, but that percent confidence level means that if we took many random samples and calculated a sample statistic, a point estimate, and created a confidence interval from each of those samples, then we would expect approximately that percentage of all of those confidence intervals to capture the true population value. That we'd have that percentage of our total of however many is to be those good green confidence intervals. On the flip side, the leftover percentage out of 100 would be those bad red ones that are not successfully capturing the true population value. And it's really no fault of our own as long as we took a random sample, but it's just sampling variability. We will occasionally get random samples that yield too small of values or too big of values. And so then we're going to end up with a confidence interval that doesn't end up working. So let's interpret the 95% confidence level specifically for our proportion example. If we took many random samples of 30 runners each and calculated 95% confidence intervals from each of those samples, then we would expect around approximately 95% of all of those confidence intervals to contain the population proportion of runners from the home state of Nebraska. Now, here's kind of the kicker again. We don't necessarily know what the true population proportion value is, what that percentage was of what percent of runners were from Nebraska.
But if we do 95% confidence and create these 95% confidence intervals, then we can be guaranteed that 95% of all of these 95% confidence intervals that we could create would contain that actual number that we don't technically know the value of. But remember, I did share that value with you previously. Now, there's going to be some times, specifically maybe, multiple choice questions on the chapter test or even on the AP exam, where they are going to try to confuse you with what that confidence level, what that percentage really means. And one very common way that they will try to confuse you is when they try to make the confidence level sound like a probability. And I would say, for the most part, using the confidence level as a probability is going to lead to an incorrect statement. But there are times, really kind of one of two instances, and we'll talk about it here shortly, when we could use the confidence level as a probability. But here's an example where it does not apply. So if they say there is a 95% probability the true proportion of all runners from Nebraska is between, and so here's an example of just one confidence interval that I created, is between 32 and 68%. Well, here's the thing about the probability with one confidence interval. Either our confidence interval is going to successfully capture the true proportion, or it's not going to. So there is no anything in between like 95%. So anytime that they use the confidence level, in this case the 95%, as a probability, then you're pretty much almost guaranteed that it's going to be an incorrect statement, especially if they make one confidence interval apply to that probability. And again, in the next slide, we'll talk about what is the actual probability that a specific confidence interval is going to successfully capture the true value.
The thing is, our confidence intervals are either going to correctly capture the true value or they're not going to capture it. But the kicker is we will never know if our confidence interval was good or bad unless we actually know the true population value. I shared with you that the true population proportion of runners from the home state of Nebraska was 44.56%. But what if you didn't know it and you calculated a confidence interval based on a random sample? Would you really know if your confidence interval was a good green one or a bad red one? And you wouldn't. That's kind of the gray, fuzzy area of statistics right now. We're just saying this is our best mathematical guess at what we believe is the upper and the lower values for successfully capturing the true population value. So the probability that one confidence interval is actually a good green one or a bad red one is either 0% or 100%. If your confidence interval does its job and it successfully captures the true population value, then the probability that it gets it is 100% because it did it. But what if it doesn't capture it? What's the probability that it captures it? Well, it would be 0%. But again, we don't know which of those two probabilities it truly is. Is it a 0% chance or is it a 100% chance? Nobody knows unless you know the true population value. Now, the only way that we could really use the confidence level itself as a probability interpretation is if you talk about selecting one confidence interval out of many or even all possible confidence intervals. So there's a slight little difference here between, do you sample many confidence intervals or are you looking at all of the confidence intervals? So we could use this statement, and this would be a correct statement. The probability we randomly select one confidence interval, one 95% confidence interval out of many confidence intervals. So again, you have to read this one of two ways. And I'll kind of hide this here. If you were going to use the word many, then you would have to say that that one confidence interval would have approximately a 95% chance of being a good green one. Now, on the flip side, you could use this interpretation and say, well, what if I selected one 95% confidence interval out of all possible 95% confidence intervals. Now what's the probability? Then you could say it's exactly 95%. So I just want to leave you with these two options here. If you want to focus on many, no, I thought I was highlighting. If you want to focus on the word many, then you have to use the word approximately because it's not covering all of them. Or if you want to say that you're going to include all possibilities, then you can say that it is exactly 95%.
In addition to misinterpreting the confidence level as a probability, there's some other ways that multiple choice answer options will try to get you to think that using the confidence level in other ways is acceptable. So here's a couple of other examples. So for instance, saying 95% of all samples taken will have a proportion of Nebraskan marathon runners between 32 and 68%. So again, they're trying to use that confidence level, that 95%, to really describe something else. So when they say 95% of all samples will be between 32 and 68%, again, this 32 and 68% was just one confidence interval that I happened to calculate. And so for them to say that 95% of all samples, there's something really special about this one confidence interval that I created is a completely incorrect type of statement here. There's nothing special about this one statement with respect to multiple samples that we could create confidence intervals from. This is just one of many. Another example is if I were to say, if many samples were taken, so this kind of sounds like the last one, then approximately 95% of all confidence intervals will be between 32 and 68%. Again, this 32 and 68% is just one confidence interval that I happen to calculate. And to say again that approximately 95% of all confidence intervals will be between these two numbers that represented one confidence interval that I created, it's making this one confidence interval sound like it's really, really special to multiple other confidence intervals, which again is 100% false.
Now, for the second part of this is where we're going to get into more of the applicable part of this. We're not going to be talking theoretical, but when we say how much spread, we're going to talk about how much is how much. How many standard deviations is really our margin of error going to consist of? So confidence intervals are based on sampling distributions, which we talked about last chapter. And one condition of working with confidence intervals is that our sampling distribution had to follow a normal distribution or an approximately normal distribution.
So now we're going to get to see a little blast from the past here. Now, we are going to hopefully have normal distributions for our sampling distributions. And back in the day, back in Chapter 2, we talked about the 68, 95, 99.7 rule, aka the empirical rule. And what's nice is this rule is connected to our confidence level, the percentage, how confident we want to be that we are capturing the true value for the population. So this is how this is going to work. So imagine we are starting to create a sampling distribution and we have our sample proportion value here. So this would be like if we took a random sample of 30 marathon runners and we calculated the percentage or the proportion of our 30 runners that were from Nebraska. So we would say that's going to be kind of the beginning of our confidence interval. And so if I wanted to create the actual interval itself to say that I'm this percent confident that the true values between this number and this number, well, now I get to tie in kind of these 68, 95, 99, 7 percentage values. So for instance, being 68% confident means that 68% of values are within one standard deviation of my point estimate, of my sample proportion value that I got from my one random sample of 30 marathon runners. If I want it to be 95% confident, which is going to be a common confidence level, then basically what we're saying is if we're 95% confident, we are grabbing 95% of values on either side of our point estimate, or in this case, our sample proportion. So we are going 2 standard deviations on either side. And Likewise, if I wanted to be 99.7% confident, which we will never really use that, but we will commonly see 99% confidence. So that would mean that we're slightly less than 3 standard deviations, right? But to be 99.7% confident means that we want 99.7% of all values around our point estimate.
So now, for the margin of error, that how much aspect is really called the critical value. And it just represents the 1, 2, and 3 standard deviations if we were 68, 95, or 99.7% confident. But how do we get a critical value that's not one of these 3 numbers? How did we do that once upon a time? Well, we had to use inverse norm in our calculators to figure out what those other values had to be. And so inverse norm was just right below normal CDF. And I'm going to show you for a newer calculator, an older calculator, what exactly we're going to have to do to get those critical values. Now, for an example, if I wanted the critical value, how many standard deviations would really 90% around the middle of our normal distribution represent? So what we want to do is we want to use inverse norm of how much one tail area is. So if we want the middle 95%, what we need to figure out is that there would be in this tail end 5%, because in the 2 tails there would be 10% altogether, and so because a normal distribution is symmetric, this one tail has 5%. So for the area you would put in 0.05, and you would leave the mean and the standard deviation as 0 and 1, because this is going to be for a standard normal distribution, which means the answer we're going to get is not only the critical value, but it's also the z-score. It's how many standard deviations are we away from the mean. Now, for the older calculator, we would put in 0.05, and then you could just stop there, or if you want to put in comma 0, comma 1, you can certainly do that as well. Now, if I put that on my calculator, I'm going to get approximately negative 1.645, yada, 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 yada. Now, the thing is, I am really just interested in the number component of this. I could care less about that negative number. So I just want to know how many standard deviations do I really need to go above and below the mean is I want to go 1.645 standard deviations. The only reason why we get a negative number here is because when we do that one tail area, we're always really going to be talking about the left end of the distribution. And the left end of the distribution is always below the mean. And that's why we got z-scores that were always negative when we went below the mean. Now, we could put in what that percentile is up here, which would technically be the 95th percentile in this scenario, but it's much easier just to use this lower tail end here. So again, in your calculator, you're going to get negative 1.645, but again, we just want to focus on the numerical part here. And again, later with our margin of error, we're going to add and subtract this many standard deviations. So in the end, who cares that it's negative? You're going to add and subtract a positive number, or you're going to add and subtract a negative number. In the end, we're still going to be doing the same math. So in the end, I want you all to try this one out. How would you get the critical value for 99% confidence? So try this one out, and we will discuss it the next day in class.